Hello, and welcome to a journey into the heart of matter. Today we embark on an adventure that will take us deep into the mysterious and fascinating world of quantum physics. This is a realm where the rules of classical physics no longer apply, and the behavior of particles can be both perplexing and awe-inspiring. We're about to explore the fascinating world of quantum physics. Imagine a universe where particles can exist in multiple places at once, and where the act of observing something can change its very nature. This is the quantum world, a place that challenges our understanding of reality. This area of science studies the very smallest things in the universe, like atoms and the particles within them. These tiny particles are the building blocks of everything around us, from the air we breathe to the stars in the sky. By understanding them, we can unlock the secrets of the universe. It can seem strange and counterintuitive, but with a little patience we can grasp its basic principles. Quantum physics requires us to think differently, to let go of our everyday experiences and embrace a new way of seeing the world. It's a challenge, but one that comes with great rewards. The quantum world operates by different rules than the everyday world we experience. In our daily lives, objects have definite positions and velocities, but in the quantum realm, particles can be in a state of superposition, existing in multiple states at once. This duality is at the heart of quantum mechanics. Objects don't always have definite locations. Sometimes things can be in multiple states at once. This is famously illustrated by Schrödinger's cat, a thought experiment where a cat can be both alive and dead until observed. Such concepts may seem bizarre, but they're fundamental to understanding quantum mechanics. Don't worry if this sounds confusing. We'll explore these concepts together. Throughout this journey, we'll break down complex ideas into manageable pieces, making the strange and wonderful world of quantum physics accessible to everyone. So let's dive in and start uncovering the mysteries of the quantum universe. To understand the quantum world, we need to start with light. For centuries, scientists debated whether light was a wave or a stream of particles. In the 19th century, experiments showed that light behaves like a wave. Think of waves on the surface of a pond. These waves have peaks and troughs, just like waves of light. Like waves in water, light can bend around obstacles and interfere with itself, creating patterns of light and dark areas. However, at the beginning of the 20th century, scientists made a startling discovery. Light could also act like a particle. This was shown in experiments where light could knock electrons loose from atoms, something only particles could do. These particles of light are called photons. Each photon carries a specific amount of energy. The more photons there are, the brighter the light. So is light a wave or a particle? The answer is both. Light exhibits wave-like properties in some situations and particle-like properties in others. This is called wave-particle duality. It's one of the fundamental principles of quantum mechanics. Imagine a coin spinning in the air. Before it lands, you can't say for sure if it's heads or tails. It's in a state of being both possibilities at once. Similarly, light exists as both a wave and a particle until we measure it. Section 5. Superposition, the cat that's both alive and dead. This brings us to another strange aspect of the quantum world: superposition. In the classical world, things are pretty straightforward. A light switch is either on or off. A door is either open or closed. But in the quantum world, particles don't follow these simple rules. This is the idea that a particle can exist in multiple states at the same time. Imagine a particle that can be in two places at once, or spinning in two different directions simultaneously. This is not just a theoretical concept, it's something that has been observed in experiments. It's like that spinning coin, being both heads and tails until it lands. When you flip a coin, it spins through the air, and for a brief moment, it seems to be both heads and tails. Only when it lands do we see the result. In the quantum world, this moment of uncertainty is extended indefinitely. A famous thought experiment called Schrödinger's cat illustrates this concept. Schrödinger's cat is a thought experiment that was devised by physicist Erwin Schrödinger in 1935. It was meant to show the strange nature of quantum mechanics. Imagine a cat inside a box with a device that has a 50% chance of releasing a deadly poison. The device is triggered by the decay of a radioactive atom, which is a random process. If the atom decays, the poison is released and the cat dies. If the atom does not decay, the cat lives. Until we open the box, we don't know if the cat is alive or dead. This is because, according to quantum mechanics, the cat is in a superposition of states. It is both alive and dead at the same time until we observe it. According to quantum mechanics, the cat is in a superposition of being both alive and dead at the same time. This thought experiment challenges our understanding of reality and forces us to reconsider what we know about the nature of existence. It shows that at the quantum level, the act of observation itself can determine the outcome of an event. Section 6. Quantum entanglement, spooky action at a distance. Perhaps the most mind-boggling phenomenon in quantum physics is entanglement. This occurs when two particles become linked, even if they are separated by vast distances. Imagine two coins flipped simultaneously. If one lands on heads, the other must land on tails. With entangled particles, if you measure the state of one particle, you instantly know the state of the other, no matter how far apart they are. Section 7. Quantum physics in our everyday lives. Quantum physics might seem like something out of science fiction. The idea of particles existing in multiple states at once or being entangled across vast distances can sound like the stuff of futuristic movies. But its principles are at work in our everyday lives. Every time you use your smartphone, stream a movie, or even just turn on a light, you're benefiting from the principles of quantum mechanics. From the lasers in our CD players to the transistors in our smartphones, quantum mechanics is the backbone of many devices we use daily. Many modern technologies rely on quantum mechanics. The microchips in our computers and the sensors in our cameras all operate based on quantum principles. Quantum computers, a new generation of computing, are being developed. These machines promise to solve complex problems that are currently beyond the reach of classical computers. These computers utilize superposition and entanglement to perform calculations much faster than traditional computers. Imagine being able to process vast amounts of data in seconds, something that would take current computers years to achieve. This could revolutionize fields like medicine, materials science, and artificial intelligence. For instance, quantum computing could lead to breakthroughs in drug discovery, creating new materials with unique properties, and advancing AI algorithms to new heights. Welcome, dear friends, to a journey into the heart of the cosmos. Today, we embark on an exploration that will take us beyond the stars, into the very fabric of reality itself. Today, we explore a concept both profound and perplexing, a key that unlocks the secrets of the universe at its most fundamental level, the wave function. This concept is not just a cornerstone of quantum mechanics, but a bridge to understanding the very nature of existence. Imagine, if you will, a universe painted not with certainty but with possibilities. Each star, each particle, each moment is a brushstroke in a cosmic masterpiece of potential. In the realm of quantum mechanics, the wave function reigns supreme. It is the mathematical heart of quantum theory, a tool that allows us to predict the behavior of particles at the smallest scales. It's a mathematical description, a cosmic code that captures the essence of a quantum system. This code is not static, It evolves, changes, and interacts with the universe in ways that are both mysterious and enlightening. Unlike our familiar world of definite objects, quantum particles exist in a haze of probability. They do not have fixed positions or velocities until they are observed. The wave function tells us the likelihood of finding a particle in a particular state, a particular place, at a particular time. It is a map of potentialities, a guide to the quantum landscape. It's like a cosmic weather forecast, not predicting a single outcome, but rather a range of possibilities, each with its own probability. Just as a weather forecast might tell us there's a 70% chance of rain, the wave function tells us the probabilities of various quantum events. It's a radical departure from classical physics, where objects have definite positions and momenta. In the classical world, we can predict the future state of a system with certainty if we know its current state. This inherent uncertainty is the hallmark of the quantum world. The famous double-slit experiment, for example, reveals the wave-like nature of particles and the fundamental role of the observer in determining outcomes. But here's the truly mind-boggling part. This wave function, this tapestry of probability, doesn't just describe tiny particles, it describes the entire universe. Every star, every galaxy, every atom is part of this grand quantum symphony. Yes, you heard that right. The universe itself has a wave function. This cosmic wave function is a testament to the interconnectedness of all things, a reminder that we are all part of a vast, dynamic, and ever-evolving quantum reality. For decades, the notion of a universal wave function remained a tantalizing but elusive concept. The idea that a single mathematical function could describe the entire universe was both awe-inspiring and daunting. It was a theory that promised to unify the vastness of the cosmos with the minutiae of quantum particles, but it seemed almost too grand to be true. How could we possibly hope to calculate something so vast, so complex? The sheer scale of the universe, with its billions of galaxies and countless stars, seemed to defy any attempt at a unified description. Scientists were left scratching their heads, pondering the seemingly insurmountable challenge. The universe, after all, is a messy place, a swirling chaos of stars, galaxies, and cosmic dust. It's a dynamic, ever-changing tapestry where new stars are born and old ones die, where galaxies collide and merge, and where cosmic dust drifts through the void. Trying to capture all of this in a single wave function seemed like an impossible task. And yet, recent discoveries have hinted at a path forward, a way to pierce the veil and glimpse the universe's quantum blueprint. Advances in technology and theoretical physics have opened new doors, allowing us to explore the cosmos in ways that were previously unimaginable. We are beginning to see patterns and connections that were once hidden from view. Scientists have begun to explore the idea that the universe's wave function might be encoded within the very fabric of space-time itself. This revolutionary concept suggests that the fundamental structure of the universe is intertwined with its quantum properties, and that by studying space-time we can unlock the secrets of the wave function. Imagine the universe as a vast shimmering ocean. This ocean is not static, it is constantly in motion, with waves rippling across its surface. These waves are the manifestations of the underlying quantum properties of space-time, and they hold the key to understanding the universe at its most fundamental level. The waves on this ocean represent the fabric of space-time, constantly rippling and evolving. Just as ocean waves can reveal the hidden currents beneath the surface, the ripples in space-time can provide insights into the quantum nature of the universe. By studying these ripples, we can begin to unravel the mysteries of the wave function. And just as the motion of ocean waves can reveal hidden currents and depths, the subtle fluctuations of space-time might hold the key to unlocking the universe's wave function. These fluctuations are like whispers from the quantum realm, offering clues to the underlying structure of reality. And this is no easy feat, mind you. The challenges are immense, and the questions we face are some of the most profound in all of science. We must grapple with the complexities of quantum mechanics, the intricacies of space-time, and the vastness of the cosmos itself. It requires us to grapple with the most profound mysteries of the cosmos, from the nature of dark matter and dark energy to the very birth of the universe itself. These are questions that have puzzled scientists for decades, and finding the answers will require a combination of cutting-edge technology, innovative thinking, and a deep understanding of the fundamental laws of physics. But the potential rewards are immense. If we can unlock the secrets of the universe's wave function, we could gain a deeper understanding of the cosmos and our place within it. We could uncover new laws of physics, discover new forms of matter and energy, and perhaps even find answers to some of the most profound questions about the nature of reality itself. The quest to understand the universe's wave function is a collaborative effort, a symphony of scientific minds working in harmony. This endeavor is not just a solitary pursuit, but a collective journey where each scientist contributes a unique note to the grand composition of knowledge. The wave function, a fundamental concept in quantum mechanics, describes the probabilities of a particle's position and momentum. It is the mathematical heart of the quantum world, and understanding it requires the combined intellect of many brilliant minds. And like any grand orchestra, it has its conductors, its virtuosos who have shaped the course of this intellectual pursuit. These leaders guide the scientific community, setting the tempo and direction of research. They inspire others to explore uncharted territories and to question the very fabric of reality. One such pioneer is physicist Sean Carroll, whose groundbreaking work on the arrow of time and the foundations of quantum mechanics has illuminated our understanding of the universe's quantum nature. Carroll's theories delve into the mysteries of time itself, exploring why it seems to flow in one direction and how this relates to the quantum world. His lectures and writings have inspired countless students and researchers to delve deeper into these profound questions. His insights into the role of entanglement, the bizarre quantum connection between particles, have opened new avenues for exploring the universe. Welcome to Cosmic Discoveries. Today we embark on a thrilling adventure to the very edge of human understanding. Prepare to explore quantum gravity, a realm where the universe's grandest forces meet its tiniest tremors. Don't worry, we'll navigate this complex landscape together, step by simple step. No confusing jargon, I promise. Just pure wonder and the thrill of discovery. Are you ready? Let's begin. Imagine the universe as a grand stage, an expansive theatre where the most intricate and awe-inspiring performances unfold. On one side we have gravity, the cosmic choreographer, dictating the movements of planets, stars and galaxies. This invisible force pulls on the fabric of space-time, weaving a dance that spans billions of years and countless light years. It's a force we experience every day, holding us to the Earth and guiding the Moon in its orbit. From the apple falling from a tree to the tides of the ocean, gravity's influence is omnipresent, shaping our daily lives in ways we often take for granted. On the other side, we have the quantum world, a realm of tiny particles, fuzzy uncertainties, and mind-boggling possibilities. Here, the rules are different, almost magical, where particles can exist in multiple states at once and teleport across space. This is where the building blocks of matter dance to a different tune, governed by the laws of quantum mechanics. In this mysterious domain, particles are entangled, influencing each other instantaneously across vast distances, defying our classical understanding of the universe. The quantum world challenges our perception of reality, inviting us to explore the depths of what is possible. Albert Einstein, a true visionary, gave us the masterpiece of general relativity. His work revolutionized our understanding of the universe, providing a new lens through which to view the cosmos. Einstein's theories were not just abstract concepts. They had profound implications for the way we perceive reality itself. He taught us that gravity isn't a simple force, but a curvature in the fabric of space-time itself. This groundbreaking idea transformed our comprehension of gravitational interactions, showing that massive objects cause space-time to bend, creating what we perceive as gravity. Imagine a bowling ball placed on a trampoline, causing it to sag. This simple analogy helps us visualize how massive objects, like stars and planets, warp the space-time around them. The more massive the object, the greater the curvature it creates. That's how massive objects warp space-time, influencing the motion of everything around them. Smaller objects move along these curves, following paths determined by the warped geometry of space-time. Einstein's theory elegantly explains the large-scale structure of the universe, from the graceful orbits of planets to the cosmic dance of colliding galaxies. It provides a framework for understanding phenomena that range from the motion of planets in our solar system to the interactions of entire galaxies. It's a smooth, predictable ballet. The universe, in its vast complexity, moves with a rhythm and grace that can be described by the equations of general relativity. This elegant theory continues to be a cornerstone of modern physics, guiding our exploration of the cosmos. Now, let's zoom into the subatomic realm where things get a bit weirder. In the quantum world, particles behave like waves, their positions and movements shrouded in uncertainty. It's like trying to pin down the location of a flickering candle flame in a gentle breeze. This inherent fuzziness, described by quantum mechanics, governs the interactions of particles like electrons and photons. It's a world of probabilities, where the very act of observation can influence the outcome. Here's the cosmic puzzle. General relativity and quantum mechanics, while incredibly successful in their own domains, seem incompatible when brought together. It's like trying to fit square blocks into round holes. The problem arises in extreme environments like the heart of a black hole or the very first moments of the Big Bang. Here, immense gravity meets the tiniest scales of the quantum world, and our current theories break down. Undeterred, physicists have proposed daring new ideas to bridge this gap. These ideas are not just theoretical musings, but are backed by rigorous mathematical frameworks and experimental predictions. They aim to unify the fundamental forces of nature and provide a deeper understanding of the universe's fabric. One such idea is string theory, which suggests that the universe's fundamental building blocks aren't point-like particles, but tiny, vibrating strings. These strings can vibrate at different frequencies, and each frequency corresponds to a different particle. This elegant theory attempts to reconcile quantum mechanics and general relativity, two pillars of modern physics that have long been at odds. Imagine a violin string, capable of producing different notes depending on its vibration. Just as a violin string can create a symphony of sounds, these fundamental strings can generate a symphony of particles, each with unique properties and behaviors. Similarly, different vibrations of these fundamental strings could give rise to all the particles and forces we observe. This means that everything in the universe, from the smallest quark to the largest galaxy, could be explained by the vibrations of these tiny strings. Another intriguing concept is loop quantum gravity, which proposes that space-time itself is quantized, made up of tiny, interconnected loops. This theory suggests that at the smallest scales, Space-time is not a smooth continuum, but a discrete structure, much like a woven fabric. Think of it as a finely woven fabric, where each thread represents a loop of space-time. These loops are constantly interacting and evolving, creating the dynamic tapestry of the universe. By understanding these loops, we may unlock the secrets of black holes, the Big Bang, and the true nature of gravity. These are just glimpses into the mind-boggling world of quantum gravity. While we don't have all the answers yet, the quest itself is incredibly exciting. Unlocking the secrets of quantum gravity could revolutionize our understanding of the universe. Imagine unraveling the mysteries of black holes, peering into the very birth of the universe, or even discovering new fundamental forces of nature. The possibilities are as vast as the cosmos itself. Thank you for joining me on this incredible journey to the frontiers of physics. If you enjoyed this cosmic adventure, please like and subscribe to Cosmic Discoveries for more explorations of the universe's greatest mysteries. Keep questioning, keep wondering, and never stop exploring the cosmos. Imagine a world where the very fabric of space and time is not smooth and continuous, but rather grainy and discrete, like a digital photograph zoomed in too closely. This is the strange and wonderful world of quantum geometry, a realm where the principles of quantum mechanics meet the geometry of space-time. For centuries, physicists viewed space and time as a smooth, continuous background on which the events of the universe unfolded. But with the advent of quantum mechanics in the early 20th century, our understanding of the universe underwent a profound shift. Quantum mechanics revealed that at the subatomic level, the world is a fuzzy, uncertain place where particles can exist in multiple states at once and where the act of observation can influence the outcome of an experiment. Quantum geometry takes this idea one step further, suggesting that the very fabric of space-time itself is subject to the laws of quantum mechanics. In this view, space and time are no longer smooth and continuous, but are instead woven together from tiny, indivisible chunks, much like the pixels in a digital image. These chunks are so small that they are far beyond the reach of even our most powerful instruments. But their existence has profound implications for our understanding of the universe. To understand quantum geometry, we first need to delve into the strange and counterintuitive world of quantum mechanics. Quantum mechanics is a branch of physics that governs the behavior of matter at the atomic and subatomic level. It is a world where energy, momentum, and other physical quantities are quantized, meaning they can only exist in discrete values. One of the most bizarre aspects of quantum mechanics is the concept of superposition, which states that a particle can exist in multiple states at once until it is observed. Imagine a coin spinning in the air. It is neither heads nor tails until it lands. Similarly, a quantum particle can exist in a superposition of states, such as being in multiple places at the same time, until it is measured. Another key concept is the Heisenberg uncertainty principle, which states that it is impossible to know both the position and momentum of a particle with perfect accuracy. The more precisely we measure one quantity, the less we can know about the other. This inherent uncertainty is not due to limitations in our measuring devices, but rather a fundamental property of the quantum world. Quantum geometry emerges when we attempt to combine the principles of quantum mechanics with Einstein's general theory of relativity, which describes gravity as the curvature of space-time. According to general relativity, massive objects warp the fabric of space-time, much like a bowling ball placed on a trampoline curves the fabric. However, when we try to apply quantum mechanics to the fabric of space-time itself, we run into serious problems. The equations of general relativity, which work beautifully on large scales, break down at the quantum level, yielding nonsensical results like infinite energies and densities. This is where quantum geometry comes in. It attempts to reconcile these two pillars of modern physics by proposing that space-time itself is quantized, meaning it is made up of discrete units, much like the energy levels of an atom. These discrete units of space-time are incredibly small, far smaller than anything we can currently observe. But their existence would prevent the infinities that plague traditional approaches to quantum gravity. One of the leading candidates for a theory of quantum gravity is loop quantum gravity, or LQG. In LQG, space is not smooth and continuous, but rather woven together from one-dimensional loops like tiny threads of fabric. These loops are not embedded in a higher dimensional space, but rather form the very fabric of space itself. These loops are incredibly small, on the order of the Planck length, which is about 10 to the minus 35th meters. To put that in perspective, the Planck length is to a proton as a proton is to the entire observable universe. At such small scales, the very notion of a smooth, continuous space-time breaks down, and the universe becomes a chaotic foam of quantum fluctuations. The loops in LQG are not static, but rather constantly interact and evolve according to a set of quantum rules. These interactions give rise to the familiar properties of space-time, such as its curvature and dynamics. Just as the motion of molecules in a gas gives rise to its pressure and temperature, the interactions of loops in LQG give rise to the gravitational field. Section 5. The universe as a network of loops. In loop quantum gravity, the universe is not a smooth, continuous expanse, but rather a vast network of interconnected loops. These loops can be thought of as the building blocks of space-time, much like atoms are the building blocks of matter. The way these loops are connected and interact with each other determines the geometry of space-time and the behavior of gravity. One of the most intriguing predictions of loop quantum gravity is that the amount of volume in a region of space is not continuous, but rather quantized, meaning it can only take on discrete values. Imagine a cup that can only hold a certain number of marbles. You can't have half a marble or a quarter of a marble. Similarly, in loop quantum gravity, space itself is granular, and the volume of a region can only be a whole number multiple of a fundamental unit. This granularity of space-time has profound implications for our understanding of the universe, particularly at the very beginning of time and in the hearts of black holes, where the curvature of space-time becomes extreme. Section 6. Quantum geometry and black holes. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. They are formed when massive stars collapse at the end of their lives, crushing their cores into an infinitely dense singularity. According to general relativity, the singularity at the center of a black hole is a point of infinite density and zero volume where the laws of physics break down. However, loop quantum gravity offers a different perspective. Because space-time itself is quantized in loop quantum gravity, there is a minimum possible volume that any region of space can have. This means that the singularity at the center of a black hole cannot be infinitely small, but rather must have a finite size on the order of the Planck length. Furthermore, loop quantum gravity suggests that the interior of a black hole is not empty space, but rather a complex and dynamic region governed by quantum gravity. Instead of collapsing to a singularity, the matter inside a black hole may reach a state of maximum density and then bounce back, eventually forming a white hole, which is a hypothetical region of space-time where matter and energy can only escape, never enter. Section 7. the Big Bang and the very early universe. Loop quantum gravity also has profound implications for our understanding of the very early universe. According to the Big Bang theory, the universe began as a hot, dense state about 13.8 billion years ago, and has been expanding and cooling ever since. However, general relativity breaks down at the moment of the Big Bang itself, where the density and temperature of the universe become infinite. Loop quantum gravity offers a way to avoid this singularity. Because space-time is quantized in loop quantum gravity, there is a minimum possible size for the universe. This means that the universe could not have started from a point of zero volume, but rather from a small, finite size on the order of the Planck length. In this scenario, the Big Bang was not the beginning of time itself, but rather a transition from a previous phase of the universe. Some loop quantum gravity models suggest that the universe may have undergone a period of contraction before the Big Bang, known as the Big Bounce. Section 8. The future of quantum geometry. Quantum geometry is a young and rapidly developing field, and there are still many open questions and challenges. However, it offers a tantalizing glimpse into the fundamental nature of space, time, and gravity. If successful, quantum geometry could revolutionize our understanding of the universe and lead to new insights into some of the most profound mysteries in physics, such as the nature of dark matter, dark energy, and the unification of all fundamental forces. The quest to understand quantum geometry is a journey into the heart of reality itself. It is a search for the ultimate building blocks of the universe and the laws that govern their behavior. While the path ahead is sure to be challenging, the potential rewards are immeasurable. Welcome to Cosmic Discoveries. Today we explore a captivating force, a force that shapes our universe. This force is quantum gravity. Imagine a force that holds everything together, from the smallest particles to the largest stars. This force is fundamental. It is quantum gravity. Quantum gravity is a mystery. It is a puzzle that scientists are trying to solve, but it is a puzzle worth solving. In this journey we will uncover the secrets of quantum gravity. We will learn about its history, its effects, and its future. Quantum gravity is the universe's foundation. It is the invisible glue that binds everything together. It is the force behind gravity. But what is gravity? Gravity is the attraction between objects with mass. The more massive the object, the stronger its gravity. Quantum gravity acts on a tiny scale, a scale so small that we cannot see it. It affects the behavior of atoms. It affects the behavior of light. Understanding quantum gravity is important. It will help us understand the universe. It will help us understand our place in the universe. Understanding quantum gravity is a challenge. It is one of the most profound and complex problems in modern physics. The quest to unify quantum mechanics, which governs the microscopic world, with general relativity, which explains the macroscopic world, has puzzled scientists for decades. It is difficult to study. It is difficult to measure. The scales at which quantum gravitational effects become significant are incredibly small, making direct observations nearly impossible with current technology. Scientists have been trying to understand quantum gravity for decades. From the early pioneers of quantum theory to today's cutting-edge researchers, the journey has been long and arduous. Each generation builds upon the work of the previous, inching closer to a unified theory. They use complex mathematics. They use powerful telescopes. Advanced mathematical frameworks like string theory and loop quantum gravity are being explored. Observations from telescopes provide crucial data that might offer indirect evidence of quantum gravitational effects. One way to study quantum gravity is to look at black holes. These enigmatic objects are natural laboratories for extreme physics, where the effects of quantum gravity might be observable. Black holes are objects with immense gravity. They are so dense that not even light can escape them. By studying the behavior of matter and radiation around black holes, scientists hope to uncover clues about the nature of quantum gravity. Another way to study quantum gravity is to look at the early universe. The conditions just after the Big Bang were so extreme that quantum gravitational effects would have played a significant role in shaping the cosmos. The early universe was a time of extreme energy. It is a time when quantum gravity would have been much stronger. By studying the cosmic microwave background and other relics from the early universe, scientists hope to gain insights into the fundamental nature of space, time, and gravity. Quantum gravity is essential to the cosmos. It governs the motion of planets. It governs the life cycle of stars. Without quantum gravity, stars would not form. Galaxies would not exist. The universe would be a very different place. Quantum gravity affects planets in many ways. It determines their orbits. It affects their tides. It even affects their shapes. Quantum gravity is a powerful force, but it is also a delicate force. It is a force that we are only beginning to understand. Section 5. Cosmic Misconceptions. Debunking Common Myths. There are many misconceptions about quantum gravity. These misconceptions often arise from misunderstandings or misinterpretations of scientific theories and concepts. Some people believe that it is a New Age idea, often associating it with mystical or spiritual practices. This couldn't be further from the truth. Others believe that it is a dangerous force, something that could potentially harm humanity or the planet. This fear is unfounded and based on a lack of understanding. These misconceptions are not true. They are myths that need to be debunked for a clearer understanding of what quantum gravity actually is. Quantum gravity is a scientific theory. It is a field of study that aims to unify the principles of quantum mechanics and general relativity. It is based on evidence gathered through rigorous scientific methods. Researchers and scientists work tirelessly to understand its complexities. It is not a threat to humanity. In fact, understanding quantum gravity could lead to advancements that benefit us all. One common misconception is that quantum gravity will allow us to travel faster than light. This is not true. The theory does not imply any such capability. Quantum gravity is a theory of gravity. It seeks to explain how gravity works at the quantum level, not to rewrite the fundamental laws of physics. It does not change the laws of physics. Instead, it aims to provide a more comprehensive understanding of them. Another misconception is that quantum gravity will allow us to create wormholes. This idea is popular in science fiction, but not supported by scientific evidence. Wormholes are theoretical tunnels through space-time. They are fascinating concepts, but remain speculative. They are often depicted in science fiction, capturing our imagination and curiosity about the universe. However, there is no scientific evidence to suggest that wormholes exist. Quantum gravity, while a profound and complex theory, does not provide a basis for such phenomena. Section 6. A Universe Unveiled. Implications for the Future. Studying quantum gravity has profound implications. It could revolutionize our understanding of the universe. It could lead to new technologies. For example, understanding quantum gravity could lead to new energy sources. It could lead to new ways to travel through space. Quantum gravity could also help us to understand the nature of time. It could help us to understand the origin of the universe. The study of quantum gravity is still in its early stages, but it is a field of study with great potential. Section 7. Beyond the Horizon, Unanswered Questions and Ongoing Research. Quantum gravity is a mystery. It is one of the most profound and challenging puzzles in modern physics. Despite the significant strides made in understanding the universe, quantum gravity remains elusive, a frontier that beckons the curious and the brave. But it is a mystery that we are beginning to unravel. Researchers around the globe are dedicating their lives to peeling back the layers of this enigma. They are driven by the quest to understand the fundamental nature of reality. Scientists are making new discoveries all the time. Each breakthrough, no matter how small, brings us one step closer to a comprehensive theory of quantum gravity. These discoveries are the building blocks of future knowledge. There are still many unanswered questions about quantum gravity. These questions are not just academic. They have the potential to revolutionize our understanding of the universe and our place within it. What is the exact nature of this force? How does it fit into the larger framework of the universe? These are questions that challenge our current scientific paradigms. How does it interact with other forces? Understanding these interactions could unlock new technologies and insights into the fabric of reality itself. What role did it play in the early universe? This question takes us back to the very beginning of time, to the moments following the Big Bang where the seeds of the cosmos were sown. These are just a few of the questions that scientists are trying to answer. The pursuit of these answers is a testament to human curiosity and our relentless drive to understand the unknown. The study of quantum gravity is a journey of discovery. It is a path filled with challenges, but also with the promise of profound revelations. It is a journey that will continue for many years to come. As we push the boundaries of knowledge, we move closer to unlocking the secrets of the universe, one discovery at a time. Section 8. Join the exploration, support cosmic discoveries. Thank you for joining me on this journey into the fascinating world of quantum gravity. The universe is a vast and mysterious place. But with every new discovery, we come one step closer to understanding our place in it. If you enjoyed this exploration into the cosmos, please like and subscribe to Cosmic Discoveries for more captivating insights into the universe and beyond. Together, let's keep exploring the wonders of the cosmos. Welcome, everyone! Today we're going to talk about something fascinating, cosmic rays. Imagine a constant shower of tiny particles raining down on Earth from outer space. That's what cosmic rays are. They're like little messengers from the cosmos, carrying information about distant stars and galaxies. These particles are incredibly small, even smaller than atoms. They zip through space at nearly the speed of light, constantly bombarding our planet from all directions. But don't worry, this cosmic rain is harmless to us. Our atmosphere acts like a protective shield, absorbing most of these high-energy particles before they reach the ground. That's a great question, and it's one that has puzzled scientists for a long time. You see, tracing the origin of cosmic rays is like trying to find the source of a river that's constantly changing direction. We know that some cosmic rays come from our sun, especially during solar flares, which are like giant explosions on the sun's surface. But these solar cosmic rays are relatively low in energy. The most energetic cosmic rays, the ones that pack a real punch, those come from much farther away. We're talking about sources outside our solar system, in the vast expanse of our galaxy and beyond. Think exploding stars, also known as supernovas. These cosmic cataclysms release tremendous amounts of energy, propelling particles to nearly the speed of light. These particles then journey across the cosmos, some eventually reaching Earth as cosmic rays. Just like there are different types of rain, from a light drizzle to a heavy downpour, cosmic rays also come in different varieties. The most common type is protons, which are the positively charged particles found in the nucleus of an atom. But cosmic rays can also be other particles like electrons and atomic nuclei. And here's the thing, the energy of cosmic rays varies widely. Some are relatively low energy, while others are incredibly powerful, carrying more energy than the most powerful particle accelerators on Earth can produce. Understanding the different types and energies of cosmic rays helps scientists piece together where they might have come from and what they can tell us about the universe. So, how do we even know about these invisible particles raining down on us from space? Well, we have ingenious ways of detecting them. One way is to use instruments called cloud chambers. These chambers are filled with a special vapor that becomes ionized when a charged particle like a cosmic ray passes through it. This ionization leaves a visible trail like a tiny contrail, marking the cosmic ray's path. Another method is using scintillators, materials that emit light when struck by a cosmic ray. By measuring the intensity and pattern of this light, scientists can learn about the cosmic ray's energy and direction. These detectors are often located in high-altitude balloons, on mountaintops, or even sent into space to get a clearer picture of the cosmic rays bombarding our planet. Section 5. Cosmic Rays and You. You might be wondering, if cosmic rays are constantly hitting Earth, do they affect us in any way? The answer is yes, but not in a way you'd probably notice. Remember our atmosphere's protective shield? It absorbs most of the cosmic rays before they reach us on the ground. However, some cosmic rays do make it through, and they can interact with the atoms in our atmosphere, creating a cascade of secondary particles. These secondary particles can reach the ground, but their energy is much lower and generally harmless. That said, cosmic rays can pose a risk to astronauts and high-altitude flights. Outside the protection of our atmosphere, exposure to cosmic rays can increase the risk of radiation-related health issues. Section 6. A History of Cosmic Discovery. The story of cosmic rays is a fascinating one, full of scientific curiosity and groundbreaking discoveries. It all started in the early 20th century when scientists noticed something strange. Electroscopes, instruments used to detect electric charge, were mysteriously discharging, even in sealed environments. This puzzled them because something in the air seemed to be ionizing the electroscopes, causing them to lose their charge. At first they suspected it was radiation from radioactive materials on Earth. But then in 1912, Austrian physicist Victor Hess conducted a series of daring balloon experiments, taking electroscopes to higher and higher altitudes. To his astonishment, he found that the rate of discharge increased with altitude, suggesting that the ionizing radiation was coming from space. Section 7. Unraveling the Cosmos, one particle at a time. Hess's discovery opened up a whole new field of research and sparked a race to understand these enigmatic cosmic rays. Over the decades, scientists have made incredible strides in unraveling the mysteries of cosmic rays. We've built more sophisticated detectors, launched space telescopes, and developed intricate theories to explain their origins and behavior. One notable discovery came in 1938 when French physicist Pierre Auger observed extensive air showers, massive cascades of secondary particles initiated by ultra-high-energy cosmic rays slamming into the atmosphere. These air showers are like giant particle detectors, spread out over vast areas, allowing us to study the most energetic cosmic rays that are otherwise extremely rare. Section 8. Thank you and keep looking up. As we continue to explore the universe, cosmic rays remain a valuable tool for probing the cosmos. They provide clues about the most extreme environments in the universe, from exploding stars to supermassive black holes. So, the next time you look up at the night sky, remember that you're being showered by a constant rain of cosmic messengers, each carrying a story about the vast and mysterious universe we inhabit. Thank you for joining me on this journey into the world of cosmic rays. Keep asking questions, keep exploring, and never stop looking up. Hello everyone, and welcome to a journey into the strange and wonderful world of physics. Today we're going to explore some of the most intriguing questions that have puzzled scientists for generations. Today we're diving headfirst into a mystery that has baffled scientists for decades: quantum gravity. This is a field that attempts to understand how gravity works on the smallest scales, where the rules of quantum mechanics dominate. Imagine you're holding a tiny marble in one hand and a giant bowling ball in the other. You can feel the difference in weight, and you know instinctively that the bowling ball is much heavier. This is because of gravity, the force that pulls everything together. It's what makes the bowling ball fall faster and hit the ground harder than the marble. But what exactly is gravity, and how does it work? Is it a force, a curvature in space-time, or something else entirely? These questions have puzzled physicists for centuries. From Newton's apple to Einstein's theory of general relativity, our understanding of gravity has evolved significantly. We have a pretty good understanding of gravity on large scales, like planets orbiting stars. This is the realm where Einstein's equations work beautifully. But when we zoom in on the tiniest particles in the universe, things get a bit more complicated. The rules of quantum mechanics start to take over, and gravity doesn't seem to fit in as neatly. That's where quantum gravity comes in. It's the attempt to reconcile our understanding of gravity with the wacky world of quantum mechanics, the theory that governs the behavior of those tiny particles. By merging these two seemingly incompatible theories, scientists hope to unlock new insights into the fundamental nature of our universe. So buckle up as we embark on this fascinating journey into the unknown. So why is quantum gravity so important? Well, it holds the key to understanding some of the most fundamental questions about our universe. Think about black holes, those cosmic monsters with gravity so strong that not even light can escape. Or the Big Bang, the moment of creation when our universe burst into existence. These phenomena are governed by both gravity and quantum mechanics. Yet, our current theories can't fully explain what happens when these two forces collide. That's like trying to bake a cake using two different recipe books, each with half the instructions missing. We need a unified theory, a quantum theory of gravity, to make sense of it all. To understand quantum gravity, we need to understand the two players involved, gravity and quantum mechanics. These two fundamental forces of nature operate on vastly different scales and principles, yet they are both crucial to our understanding of the universe. Gravity, as we've discussed, is the force of attraction between objects with mass. It is the reason why apples fall from trees and why planets orbit the sun. This force is omnipresent and affects everything with mass, no matter how large or small. It's what keeps us grounded on Earth and governs the motion of planets and stars. Without gravity, the universe as we know it would be a chaotic place with no structure or order. On the other hand, quantum mechanics describes the bizarre behavior of matter and energy at the atomic and subatomic levels. This realm is governed by principles that often defy our everyday experiences and intuitions. Here, particles can be in multiple states at once, and their behavior is governed by probabilities rather than certainties. This means that at the quantum level we can only predict the likelihood of an event occurring, not the exact outcome. The problem arises when we try to combine these two theories. Gravity and quantum mechanics each work exceptionally well within their own domains, but they seem incompatible when we attempt to merge them. Gravity, as described by Einstein's theory of general relativity, is a smooth, continuous force. It bends and warps the fabric of space-time, creating the gravitational effects we observe. Quantum mechanics, however, describes the universe as being chunky, with energy and matter existing in discrete packets called quanta. These quanta behave in ways that are fundamentally different from the smooth, continuous nature of gravity. Black holes are perhaps the most dramatic example of where our current understanding of gravity and quantum mechanics breaks down. These enigmatic objects are formed when massive stars collapse under their own gravity, creating a region of space-time where gravity is so strong that nothing, not even light, can escape. At the center of a black hole lies a singularity, a point of infinite density and zero volume. Here all our known laws of physics crumble, and we need quantum gravity to understand what's truly going on. Another area where quantum gravity comes into play is in the study of the Big Bang. According to the prevailing cosmological model, our universe originated from an extremely hot and dense state about 13.8 billion years ago. In the first moments after the Big Bang, the universe was incredibly small and incredibly dense, a perfect setting for quantum gravity effects to dominate. By understanding quantum gravity, we hope to unravel the mysteries surrounding the Big Bang, such as what caused it and what happened in the very first fractions of a second after the universe came into being. So how do we go about finding a theory of quantum gravity? One promising candidate is string theory. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. Just like a guitar string can produce different notes depending on how it vibrates, different vibrations of these strings correspond to different particles and forces, including gravity. While still a work in progress, string theory offers a framework for unifying gravity with the other fundamental forces of nature and could potentially unlock the secrets of quantum gravity. While we don't have all the answers yet, scientists are actively searching for evidence of quantum gravity through a variety of experiments and observations. These include studying the behavior of ultra-cold atoms, looking for subtle variations in the cosmic microwave background radiation, the faint afterglow of the Big Bang, and even attempting to create miniature black holes in particle accelerators. Each of these experiments provides valuable clues that bring us closer to understanding the quantum nature of gravity. The quest for quantum gravity is one of the most challenging and exciting frontiers in modern physics. This elusive theory aims to bridge the gap between general relativity, which governs the cosmos, and quantum mechanics, which rules the microscopic world. It's a journey into the unknown, driven by our insatiable curiosity to comprehend the fundamental workings of the universe. Scientists around the globe are tirelessly working, using advanced technology and innovative methods to unlock the secrets of quantum gravity. While we haven't fully cracked the code yet, the pursuit of quantum gravity has already led to groundbreaking discoveries and pushed the boundaries of our scientific understanding. From the behavior of black holes to the nature of space-time itself, each discovery brings us one step closer, and who knows what amazing revelations await us as we delve deeper into this fascinating realm. The potential to revolutionize our understanding of the universe is immense, and the journey is just as thrilling as the destination. Thank you for joining me on this adventure into the world of quantum gravity. Your curiosity and support fuel this incredible quest for knowledge. If you enjoyed this exploration, please give the video a thumbs up and subscribe to the channel for more mind-bending physics explorations. Stay tuned for more exciting discoveries and insights into the mysteries of the universe.